Today I would like to talk about my research title on speech enhancement using adaptive threshold on dual tree wavelet, complex wavelet domain. So this is today's agenda. I'll move on to the introduction. So actually, why do we need speech enhancement? Many of the speech processing systems which have outstanding performance in laboratory environment often degraded by noise signal in practical situations. Speech enhancement is therefore very important in signal processing, especially in electronic systems such as hearing aid system, the walkie-talkie, and computer-based speech recognition system. Therefore, this speech enhancement research is carried out to improve the speech quality and intelligibility using an denoising algorithm. So, what do we mean by noise? Noise is a natural occurrence which is added to speech signal, and these are the most common type of the noise in our surrounding. This is white noise, which is like a hissing sound with a low spectral density. And next, there will be this car noise, and we have also the street noise, and we have Weber noise. So what do we mean by Weber noise? It's actually a human background noise where we have two or more people talking at the same time. Next, this study introduces a wavelet transform to decompose noisy signal for analysis. In this case, a dual tree wavelet complex wavelet transform is used. This is because it's flexible time frequency analysis technique which is suitable for both stationary and non-stationary noise. And also, we are using this Tietze energy operator which is used to approximate the adaptive threshold. This is real-time realizable because it doesn't require any prior knowledge of the signal-to-noise ratio. The aim of this study is to develop a reliable solution which is effectively suppress the background noise of a noisy speech and maximizing the intelligibility of the speech signal without any prior knowledge of the characteristic of the speech. So we can actually apply this algorithm in a real environment, such as those walkie-talkie and the hearing aids. We'll move on to the methodology. And this is the overall system block diagram. So first of all, we'll have a clean speech signal, which is the original ideal signal which is wanted. And then we'll add a noise signal in order to create a noisy speech signal for our analysis. And we'll have this dual tree complex wavelet transform to transform it into a various subband for our analysis. And we'll have this adaptive threshold to be applied on the respective subbands to remove the unwanted noise. And at the end, we'll reconstruct the noisy subband into the original speech signal using this inverse dual tree complex wavelet transform. And we'll obtain the noise speech signal, which is a clean speech signal. So we'll move on to the adaptive thresholding detailed block diagram. So first of all, we'll have this noisy subband. Okay. This is decomposed by using this dual tree complex wavelet. As you can see, there's a complex wavelet because it's formed by a real tree and also the imaginary tree. So this will be the low pass coefficient, where we'll get the low pass coefficient by using a low pass filter. The important part of this dual tree complex wavelet is that the low pass filter for the imaginary tree and real tree must be different. Else there will no advantage is gained if both of them are of the same coefficient. So we will further decompose the low low frequency component into its various subbands in order to further analyze the detailed component of the signal. So in this case, we are using a 3-level decomposition. This is because if there's any lower level of the decomposition, we won't get the detailed time resolution to analyze our result. And any further decomposition will cause too much of a time needed to process the speech signal. Okay. As you can see, in the end, we'll only process 8 of the subbands, which is made up of 6 high-frequency components and 2 low-frequency components. Next one, we'll combine the subband with the TAJ energy operator in order to calculate the TEO coefficient to estimate. The TAJ energy operator is used to enhance the discriminability between the speech and noise. It's used to estimate the energy of the clean speech signal. The TAJ energy operator coefficient is said to be suitable for real-time processing. This is because there's only 3 samples of data is needed for each computation. So it can be applied in our real-time processing. So we will move on to the masking of the TAJ energy coefficient. As we know, the speech signal is a continuous signal, and for our TAJ energy operator coefficient, it will create some discontinuity of the signal. Therefore, we are introducing this masking of the TAJ energy operator in order to improve the continuity of the signal. This coefficient will help us to smooth the signal so that the unvoiced segment of the speech signal is retained. Okay. In order to perform the masking of the TAJ energy operator, we will have this Hamming window to convolute with the TAJ energy operator. And our research showed that a longer window length will amplify the noise amplitude. Therefore, we are going to use different length of the Hamming window for different subbands of the frequency. Next, we'll have this universal threshold calculation. As proposed by this the complex wavelet package, we need to use this formula. So we are using this formula with the assumption that there is no any noise variance in our speech signal. But in practical case, there are a lot of noise present, so we are going to modify this assumption by adding in this noise variance to our formula. We'll move on to the adaptive threshold computation. What do we mean by adaptive? This is because adaptive means that we'll apply a higher adaptive threshold to a signal which is where the speech signal is weak, which means that the noise is dominating. And there will be a lower threshold value for the period where the speech signal is strong, where the speech is dominating. And we are using soft thresholding instead of hard thresholding for our adaptive threshold. This is because we need to make sure that the speech signal is smooth and still have the continuity at the end of the decomposition. So soft thresholding basically reduces the value below the threshold value to 0 and also to shrink all the remaining values with the threshold value calculated. So at the end of the decomposition, we will need to reconstruct the speech signal using the inverse of the dual tree complex wavelet as shown. So in the end, we'll get back the original denoised speech signal which we have already performed the adaptive thresholding on it. So this is the ideal case where we actually obtain the noise speech signal from the noisy speech signal. So this is the comparison between the newly proposed method, which is our research title, with the original method available out there. So we actually improved it by looping the iteration for 9 times compared to the other method, which they only process it for one. And there's also a different length of Hamming window are used in our project. And we also threshold the low frequency component, whereas the other method, they do not threshold the low frequency component. So this is the result where we can obtain from decomposition of the using dual tree complex wavelet transform. So these are the 8 subbands where we obtain. So as you can see from here, the TAJ energy coefficient is approximated and is simulated using MATLAB. So this is the clean speech signal. And as you can see, the TAJ coefficient actually captures the clean speech signal from the noisy speech signal. So this is the TAJ energy coefficient thus in capturing the clean speech signal. This is when the signal to noise ratio is considered high. So this is when the signal to noise ratio is poor. The TAJ energy operator is actually failed to capture the wanted clean signal. So in this research, we found that this method is only suitable for those where the signal to noise ratio is high. So we are increasing the number of iterations of our processing. This is because we found that the higher the iteration, the signal to noise ratio of the output is further improved. So from this graph, we found that the improvement have been is saturated when it reached the 9th iteration. Therefore, in this project, we chose this 9th iteration. As you can see, the increment is already saturated after that. So this is the result where we compare with the other method. As you can see, the signal to noise ratio of the proposed method is far higher than the other method. So we actually can conclude that this proposed method is better than the other methods available out there. And this is we actually calculated the result using 30 valid samples, which we obtained from 4 females and 4 males. And we actually added the noise signal to the clean speech signal. And this is the result tested. And you can see that the signal to noise ratio of the proposed method is higher than all of the methods out there. So this is the test result for the white noise. And 100% of the noise signal achieving a good quality of speech signal, which is above 5 dB. And this is the result for the Weber noise. There is also an improvement of average of 1.8 dB using the new proposed method compared to the others method, we have only minimal amount of the improvement in the signal to noise ratio. And this is the result for a street noise. As you can see, there's a big difference between the proposed method and the available method as well. We have a very significant increment in the signal to noise ratio in our proposed method. And this will be the result for the siren noise as well. So, in conclusion, the proposed method is actually successfully achieved 100% of all speech signal having a good quality of speech, which is above 5 dB. There is also an average of 35% improvement compared to the other two methods. And the proposed method is preferable than the other two methods in the presence of non-stationary noise. There is only very small amount of increment in the other two methods when there is a non-stationary noise. So we are able to achieve a 3-level dual tree complex wavelet transform to decompose the audio signal for further processing. And there's a new adaptive soft thresholding method is created with all of these modified parameters as mentioned before. We have this Hamming window, and also to include the scale adaptive thresholding for the low pass coefficient, and increasing the algorithm iterations, and also high frequency subband threshold on every iteration. As mentioned before, we are using a total of 30 speech samples recorded from 4 males and 4 females, and each of them are degraded with 4 types of noise, which is provided by our industry partners, Motorola Solutions, for their testing as well, for the real environment test for their walkie-talkies. The evaluation shows that the new proposed method is better than the other method in terms of the noise suppression and also the intelligibility. The limitation of this project is that it's less suitable for the low input SNR signals because it's difficult for the teenager energy operator to estimate the energy of the clean speech signal. And it also has limited access to the low frequency subband. Due to the dual tree complex wavelet transform, we only have 1 low frequency subband for each of the 3. As we know, the low frequency subband contain most of the energy signal. So we actually need to further analyze the low frequency subband in order to properly remove most of the noise in low frequency subband. So as for the future enhancement, we are found out an alternative way to decompose the signal instead of using a dual tree complex wavelet. This is the new algorithm where we can replace the dual tree complex wavelet by using this wavelet package transform for decomposition. Because this method not only decomposes the low frequency, but also decomposes the high frequency component as well. So in the end of the decomposition, we can actually have more access to the low frequency subband. So we can actually have more access to it, and we can analyze the signal better, and we can remove most of the noise if we are using this wavelet packet transform. So any questions?
Any questions from the floor?
Personally, I like your presentation. I'm not from engineering, but I can understand what you're saying. So congratulations. However, you could give more practical examples, right? Like, what do you mean by low frequency? Give us an example of where this low frequency sound comes from, or maybe play a low frequency sound for us, or a high frequency sound. That will give us more perspective of what you're saying, right? However, it's good.
Have you have listen on the what type of noise you're actually testing on it?
Right. That's an audio.
Yeah. Play back some sounds maybe. Give you a minute.
frequency 我还懂，它 stationary sound 和 stationary sound 不一样。
What noise is that?
So this is Weber noise, where we have two or more person talking at the background. So I'll play back the result that I got from my denoise signal. So if you can listen, the difference is that the background noise is actually removed from the noisy speech signal. So I can do a playback another time for you to differentiate the noisy signal and the clean signal. So this is the noisy signal. And this is the denoise signal. And I will play back the other method that proposed by others. Okay, this is their denoise signal. So as you can see, the proposed method is far better than the others method out there, where the background noise is reduced. Although there is still some noise out there, but we found out that it can be further enhanced by using the new proposed method.
Thank you. I would also like to comment on your presentation. I'm also not from an engineering background, and I totally hate science.
Okay.
But your presentation makes me wonder whether I should have taken science in the first place. Because that sounds absolutely easy to understand, very much useful for the world, and there's a huge contribution here. However, I would just like to ask you, have you actually developed a prototype based on your research to actually place this denoising adaptive threshold technology into, let's say, a hearing aid or a walkie-talkie? Have you actually done a prototype?
No.
Just out of curiosity.
This is just a research project where we're actually looking for the best algorithm to denoise it. So this is just a first part of the project, which is to find an algorithm which is best for the noisy signal. So this we actually done based on simulation using MATLAB.
Thank you very much. Excellent.